Hey guys, it's just me tonight. We're doing a little divide and conquer with the last bit of module 4. So I'm just going to jump right on in and hopefully not do any stupid jokes too much. So let's do 4.10. I'm going to introduce you to the binomial distribution. We have a couple of learning objectives here. We're going to first estimate the probability of a binomial random variable, but we got to first figure out what that is using the simulation. And then we're going to calculate some probabilities based on that distribution we come up with. So here is the essential knowledge for 410. We're going to use the rules of probability to construct what's called a probability distribution. That's the distribution of the results of what can happen in an experiment. And a binomial random variable is what we're going to be talking about in 410. A binomial counts how many times we have success when we do a bunch of independent trials. So we're going to have a situation where we have something that we want to happen and something that we don't want to have happen. If it's either going to be that or not. So it's success or failure. And there's a probability, a fixed probability P of success on every trial. We'll see. This will make a little more sense when we get into an application. If there's a 70% chance the outcome I want to happen happens, then the complement 1 minus 70 or 30% would be the probability that it wouldn't happen or that a failure. So we're going to have it be yes or no, black or white. We just call it success or failure. Okay. And there's a formula for that, but we're going to build it and you will never have to actually use this formula. It's nice to know, but we'll talk about it. So here's a scenario. I know you probably, like me, have been getting more packages in the mail in the last few months. I've been using Amazon and a couple other services because not being able to travel as much. So we're worried about on-time delivery. I ordered my new computer. When I got this job to work with Lakeside and teach you, I ordered a brand new MacBook Pro because I wanted to be able to have a computer dedicated for this job. And it was late. FedEx messed up. And they claim that their shipping company, they claim they're going to have 90, actually FedEx claims higher than that, but let's say a company claims 90% of its shipments arrive on time. How would we know that? How can we verify that? How can we test that claim? This is an idea or an example of success or failure. If I'm working for a delivery company, I get the package there on time or I don't. My computer was a failure. They got it to me 3 days late. It happened to be the same time a hurricane was passing through, but I don't care. I wanted my computer. It was late. It was a failure. Okay. What we could do, the way we could do this is test it is we could randomly select 100 shipments. We could use some kind of random number generator, collect 100 shipments and see if they arrived on time or not. How many would you expect if we sampled 100? Well, obviously, if their claim is true, we would expect it to be about 90. But if it were 89, if it were 92, if it was 87, if I was the manager of the company, if that was close to 90, it wouldn't be a red flag. But if they claim 90% and we sampled 100 and only 50% arrived on time, that's a red flag. Okay. And if I were the manager and they were only getting 50, then we'd have to have a conversation and do some work. Okay. So how close is close? And that's the idea of what we're talking about, okay? So here's the idea of a binomial random variable. And I've kind of already alluded to it. The first thing, we perform a bunch of independent trials. We had a bunch of independent deliveries. We can flip a quarter 20 times, okay? Or a fixed number of times. And every time I flip that quarter, it's either heads or tails. So if I'm wanting heads, I have a fixed probability. That's a key piece, is that it's a fixed probability each time, okay? So there are some conditions for this to be met. First, there's only 2 outcomes. I get what I want, success, or I don't, failure, okay? So I'm looking for success or failure, and that will vary from application to application. It could be on-time delivery. It might be, certain political candidates winning, okay? Certain parties or, your success might be different than somebody else's success, by the way, depending on how you conduct the experiment. Each trial is independent. The fact that my package on my computer was late did not possibly affect your package from FedEx. You might have gotten a package that was just fine. And I've gotten other packages from FedEx that were fine. I just happened to, my big, fancy, new, shiny computer was late. All right. But that didn't have any impact on your delivery or the delivery I got from them the other day that had some DVDs in it that I went, yeah, I still buy DVDs. Let me be. All right. There are a fixed number of trials. We're going to experiment and we're going to do it a certain number of times. And the probability is each time is success is the same. Okay. So none of them touch each other, none of them influence one another, and the probability is the same each time. You can remember binomial as bins, B-I-N-S. It's that binomial bins. These are conditions for it. Okay. So let's look at a couple examples. If I toss a coin 10 times and count the number of heads, is that binary? Yes, it's heads or tails. Is it independent? Is every toss going to have no influence on the other? Yes. Is there a fixed number of times? Yes, 10. Is there a fixed probability of success each time? Yes, it's 50%. So this one meets the condition of a binomial. If I were to count the number of heads when I flip a coin 10 times, that would meet the criteria of being a binomial. Okay. So the next one, I deal 10 cards from a shuffle deck and count the number of red cards. I have fixed now, or now is it success or failure? I have red or black. Yes, it's binary. Is it independent? Does one trial influence the other? And that's a failure right there. Because once I deal out the first card, I have a 50% chance of getting red. What happens once you get that first card? It's either red or black, right? But then I only have 51 cards left. There was 52 originally, but once I take one away, I'm changing the probability. So this one would be no, because the probability is changing and they're not independent, okay? The third one, two parents with A and O blood types want to have children with O blood type. I don't know why, maybe that's genetically better. What's missing with this one or what's wrong with this one is we don't know how many kids they have. There's not a fixed number of trials. So their conditions are those bins, those four letters, B-I-N-S, and they need to all be met for it to be binomial, okay? So let's go back. We're going to examine Miss Young's free throws again. I know we're probably sick of listening to her brag about how good a free throw shooter she is, but earlier she claimed to be an 80% free throw shooter. And if we believe this is true, if we just accept the fact that it's true, what's the probability of her making 5 out of 5? Well, she has to make all 5, and we're going to assume this is true. So what we're going to do is this is going to be a binary because we have success or failure. She makes it or not. Each free throw, it doesn't influence the other. Now you might argue in her mental state or whatever, but no, we're just going to assume every free throw is independent. There's a fixed number of trials, 5, and there's a fixed probability of success. We're assuming 80% free throw on every shot. Okay, so for her to make 5 in a row, she'd have to make the first one, which is an 80%, the second one, which is an 80%, the third one, 80%, fourth one, 80%, and the fifth one, 80%. And when we're doing a bunch of trials like this, we multiply them, 0.8 times 0.8 times 0.8, 5 times. And when we do that, so the way we're going to annotate this is the probability of success, 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 success. 5 successes in a row, in sequence. So it's 0.8 times 0.8 times 0.8 times 0.8 times 0.8. I've already done the calculation. It's 0.32768. That's her probability of making 5 free throws in a row if she is truly an 80% free throw shooter. Okay? So if we asked her to go to the gym and shoot 5 free throws many, many times, shoot 5 free throws many, many times, she would make 5 shots approximately 32.768% of the time. That's that context we always got to talk about. Okay? So that one wasn't so bad. What about the probability of her making 4 free throws? Well, she has to miss one, right? She can miss the first one and make the last 4. She can make the first one, miss the second, and then make the last 3. She can make the first 2, miss the second, and make the last 2, and so on. This one's a little bit harder. Okay, I started with the easy one. So what about the probability of her making 4 free throws? Well, She makes the first 4, then misses the last one. You see success, 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 failure. So that would be 0.8 times itself 5 times, and then failure on that 4th or the 5th time. And that happens about 8% of the time. Okay, that's one way it could happen. Another way she can make 3, miss 1, then make the last one. Okay, so see how I did that? Success, 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 failure, then success. And again, that would be 3.8s multiplied, then a 0.2, and then a 0.8. And oh, look, it comes out to be the same 0.08, 192. She can make 2, miss 1, and then make 2 more. So success, success, failure, success, success. And get 0.8 to the second power times 0.2 times 0.8 to the second power. And again, we get the same thing. I think you see where I'm kind of going here. The 4th way she could do it is she could make 1, miss 1, then make the last 3. And that also has the same probability. She could miss the first one and then make the last 4. And that would also have the same probability. They all have the same probability because there were 4 0.8s multiplied together and a 0.2 multiplied together. So that is always going to be 0.8 to the 4th times 0.2, but it has to be the number of ways. And this is something called a combination. Okay, so the probability of 4 successes turns out, if I add those all up, to be about 0.4096. So she took 5 free throws many, many times. She would make 4 approximately 40.96% of the time. Okay, and that's where this comes from. We're going to get the number of successes, the probability of success times the number we're looking for, and the number of failures raised to, oh, that formula is wrong. That should be n minus, I think that's wrong. Go back. I think I did it wrong here too. Yeah, it should be n minus p. I have to double check that. N minus x. Okay, this should be n minus x. Okay, so if this were 4, if this were 4 and out of 5, right? So we're talking about, so we have 5 combined 4. We would have 4 here and 5 minus 4. So I'm sorry, that formula is wrong in the slide. I'll fix it on the slide when it's posted, but in the video, I'm not gonna, so it should be n minus x there, okay? Sorry about that. So let me just jump out of this real quick because I'm gonna use the calculator anyway, okay? So that formula, but like I said, you're never gonna have to use that formula. This formula should be right here, n minus x, okay? But the cool thing is there is a way to do it in the calculator. It's called Binomial PDF. So I was gonna go to the calculator anyway. And even though that formula I had that wrong, and I'm so sorry about that. It's my first mistake ever. The cool thing is I'm gonna make up for it because I'm going to use the calculator every time. I'm not gonna I need to write this out, okay? But I wanna show you how the calculator would come up with this 0.8 or 0.4096 for you pretty quickly, okay? So I'm gonna leave the problem up there and I'm gonna make a new document and add a calculator page. So what we're gonna do is go to menu and go down to probability and go to distribution. So it's probability, menu 5. And if you scroll down, you'll see all the way down here, oops, sorry, I went too far. Binomial PDF, it's option A. And so what I wanna do is I'm gonna pick binomial PDF because it's gonna tell me the probability of getting one number out of a fixed number of trials. How many trials did we do? We did 5. We want the probability of success for Miss Young's free throws was 80%. And the value we wanted was 4. So when I hit okay, it finds the binomial probability of 4 successes out of 5 trials, and it gives me the answer, okay? So if I wanted to do that same thing again and again, I like doing it that I don't want to go back in the menu every time. I can go back here and I could change that 4 to a 5 and it should give me, I think it was 0.32 something. Yep, that's the same number we had a moment ago. And if I continue on, so what we're going to do, and again, we're now down to here. What we're going to do is calculate 3, 2, and 1. Okay. So using my calculator again, the nice thing is you can go back up and grab that command and press enter and then just simply edit it. So let's find the probability of getting 3 out of 5. And that happens about 0.248. Okay, so let me write that down here. And what I'm doing is I'm making a distribution here, okay? And it's 2048, okay? Let's, excuse me, let's go back and do 2. So I'm gonna change that 3 to a 2. This is the probability of her getting 2 out of it. If that happened, she would get, if she shot 5 free throws many, many times, she would get 0.05. 1, 2. Okay. And let's go back and see what her probability of getting 1 would be. And we replace that 2 with a 1. And that would be only 0.0062. And then finally, if we go back and do the probability of getting 0, that means that she would miss them all. If she was truly an 80% free throw shooter, the chances of her missing all 5 free throws would be 0.00032. Okay. And what we're looking for now, why I went and calculated all of those, we've been talking about the 5% rule. We're kind of setting you up for something that's coming down the line. That's a 3. Is if we are trying to prove, if Miss Young claims that she's a 80% free throw shooter, and so we go test her, we take her to the gym and make her shoot free throws. If something occurs that would only happen less than 5% of the time, we have reason to doubt the claim. And that's kind of that's a big, big idea in statistics. We've been talking about that for a while. So if Miss Young said, oh yeah, I'm an 80% free throw shooter, and we took her to the gym and she only hit 1 out of 5 free throws, we would have cause to believe that she's not telling the truth. So if she got 0 or 1, we'd have reason to doubt her. Okay. It's not proof. Statisticians will never say it's proven, but we have reason to doubt her. Okay. So that's a big deal. Okay. So let me move on down to the, let me get back in the slideshow because that's all I think I need the calculator for right now. And if we go to the next slide, we have that values. I already filled them in, and we can make a plot of them. We could get a histogram of the her free throws. And so we would see that 4 was the most likely outcome, which is not unexpected, right? And 5 would be very likely, but anything that happens 0 or 1% of the 0 or 1 would be very unlikely if she was truly an 80% free throw shooter. Okay. And that wraps up 4.10. There's 3 Khan academies there for you to take a look at. And sorry, it was just me, but we're kind of dividing and conquering up these last few chapters or sections. All right. Have a great day.